Kyriakos Georgiou, and I am a postdoctorate researcher at the University of Napoli under Professor Konstantinos Sietos. In this work, I will be presenting Fredholm Neural Networks. As a motivation, we have seen that deep neural networks and the general area of scientific machine learning has been very useful for solving integral equations as well as ordinary and partial differential equations. However, deep neural networks also exhibit some disadvantages. Specifically, there is a lack of explainability, and furthermore, they also exhibit large errors, especially near the boundaries of such equations. The research question that we examined was how can we connect established numerical schemes to deep neural networks, specifically for the family of integral equations. We consider Fredholm integral equations, which are of the form given in equation 1, and we are looking at the cases where the integral operator is either a contraction or non-expansive. In such cases, it is well known that with successive approximations, we can reach the fixed point of the integral equation, which is also its solution. This is known from Banach's fixed point theorem. The most general way of applying the successive approximation method is by the Krasnoselski-Mann iteration. However, what we can see is that each iteration in the Krasnoselski-Mann method is actually the calculation that goes on in the interior of a neural network. We see that we can decompose the discretized version of the integral operator into the result of the previous iteration times a weight plus a bias, which is exactly what calculations occur inside the neural network. Therefore, applying this m times reaches the mth iteration of the successive approximations and is identical to the output of a deep neural network with m hidden layers. This is the Fredholm neural network, and our theorem shows that we can construct these neural networks for any type of function which is a solution to this Fredholm integral equation. In this way, we connect integral equations to established numerical schemes, and therefore we also can know a priori error bounds and how many layers are required to achieve a specific level of accuracy. Fredholm neural networks can also be generalized to nonlinear Fredholm integral equations. This can be done by simply creating an iterative scheme that transforms the nonlinear integral into a linear integral. In our examples, we showed that we can apply this to Fredholm integral equations in the linear and nonlinear case with very good results. Most importantly, however, we were able to apply these to the PDEs. We considered the example of a Laplacian with a circular boundary, and we showed via potential theory and boundary integral equations that we can use Fredholm integral equations to reach the solution of this PDE. Specifically, with the boundary integral equation, we reach a Fredholm integral equation which can be solved using the Fredholm neural network. What is then required to retrieve the solution of the PDE is simply to use potential theory, which adds one final layer to our neural network and retrieves the solution to the PDE. We applied this and showed that it obtained very good results of the power 10 to the minus 7, which were better than the results in finite difference schemes. Furthermore, these results were consistent throughout the domain and the boundary of the problem. In this way, we not only can understand how the deep neural network is constructed, but we are also able to achieve very good accuracy results. We hope that this will bring further research into the methods of explainable AI. Thank you very much.